had a chance to work on board of the research vessel Falcor earlier this year. Dr. Charlie Paull, he's a prolific marine geologist who participated in over 35 oceanographic research cruises. On 14 of them, he has been a co-principal investigator. He has had a chance to work on board of our vessel, and it's a wonderful example, as you will see, that encompasses topics of several of our conversations yesterday and today, being able to explore and research geology of the seafloor, utilizing the most innovative instruments, using the vessels and vehicles. And I'd like to welcome our speaker, Dr. Charlie Paull, for the presentation that is entitled Surgical Exploration of the Seafloor using a combination of multibeam, autonomous underwater vehicles, and remotely operated vehicle data. Please, Charlie, take it away. The floor is yours.
Well, thank you, Victor. It's a pleasure to be here, and I was asked to address the question of multi-beam data, and have chosen to do that by showing 3 examples of how multi-beam data, fits into the repertoire of science and how we utilize it. And frankly, one of the keys to it is multi-beam data collected from a surface ship like the Falcor is simply a roadmap that enables other understanding to proceed. Now, the first thing I'd like to sort of acknowledge about this is all science consists of a lot of collaboration, and I'd like to point out that I'm talking about 3 areas, and Dave Caress, who's here, is one of my principal collaborators for all 3 of these studies, and there are a whole lot of other people that deserve to be acknowledged in this effort. But what I'm going to do first is talk about a Falcor cruise in the Gulf of Mexico. I'm then going to move on to another example of multi-beam data collection and how it stimulated scientific thinking in the Arctic. And then I'm going to come back closer to home to Monterey and point out some of the progress we've made in new systems that we're in the process of developing. Now, the first science cruise, explicitly for science, on the Falcor was cruise 007. It took place in March 2013, and it was simply dedicated to the surface ship multi-beam mapping using the really high-quality multi-beam system that's on the Falcor. And so we were mapping in the Mexican sector of the Gulf of Mexico, on the northern edge of the Yucatan platform in an area which is called the Campeche Escarpment. So now, being based in science here, when one conducts a survey like this, there's always a reason why. So the question is, why are we surveying here, and what were we doing it for? And in this case, the motivation for this goes back to the Cretaceous Paleogene boundary. Now, this is one of the most profound events in Earth history. I, as a child, got interested in this, and one of the reasons that I'm a scientist now is my fascination with the dinosaurs. Of course, they died at this boundary, and this has been one of the things that has stimulated kids to think about things and enter science for a long time. Tremendous interest in this particular event. Now, it resulted in the death of approximately 3/4 of all animals and plants on the Earth that we know of, and the generally accepted cause of this is that a meteorite impacted with the Earth, or a comet, in what is now the Yucatan platform. And this was a really bad day. The impact structure in the crater underlies and kind of straddles the coastline of the Yucatan today. It is a very large crater in the subsurface, about 180 kilometers in diameter. And when it impacted, it blew out material from the area over and produced the global ejecta pattern. But one of the things that modelers have come up with is this impact event released something on the order of 1.5 times 10 to the 24th joules of energy. Now, frankly, it's a big number, I understand, but I don't quite understand that number. It's not tangible to me. So if one wants to put this into something that has some human perspective to it, this amount of energy could be compared with little boy atomic bomb that devastated Hiroshima. It turns out that this is 2.2 billion little boy atomic bombs. Big event. Now, I can't conceptualize that well either, and the people that model the impacts, the structures, which give it a perspective of deciding what it's like in your own hometown. And I've chosen a radius of 3,500 kilometers in this, which incidentally corresponds with Mountain View, California, where Google Earth is. And if one thinks about what would happen there, which would pretty much encapsulate most of North America as well, we would have an earthquake that occurred in that area about 12 minutes after the impact that would be equivalent to a magnitude 10.3 to magnitude 12 earthquake at this distance. I might point out that's 30 times larger than the largest earthquake that man has recorded, with the Chilean earthquake. And this was followed by a series of other individually devastating events that would take place minutes and hours later. All of them would be life-threatening events. But moving closer to the source of this, that's nice. Well, it'd be nice to get the internet. They're aggressive. Closer to the source, the impact is believed to have melted through the entire Earth's crust, down to a depth of more than 30 kilometers. It obviously fractured the rocks in a very regional way. It produced the global dust layer, which is how we tracked down this event to this location. But it's since been buried by about 1 kilometer of tertiary sediments. So it's sort of hidden in the subsurface, and there are some boreholes that are nearby that have been drilled from into the deposits, but most of what we know about the crater itself and the impact has come from remote sensing, like this gravity map that's shown in this figure. And there really are only a few near boreholes. Computer doesn't like this.
Lower left corner, maybe?
I think this is an autosave, but while this is the boreholes that are nearby are shown in this illustration in these triangles, and there are 3 of them that are inside the crater. These have more than 500 meters of ejecta deposits that are in them. But if one then moves from there to the nearest deposits that are exposed on land, that little blue arrow points out where the first deposits are of this event. They're 500 kilometers further to the south, and at that site, I've got some sort of colossal failure here. At that site, those deposits are on the order of 10 meters thick, 500 kilometers away. And the deposits consist of fragments of limestone that have been apparently blown through the sky because they're not on limestone deposits, and they're held in a matrix that came down of sort of siliceous material, which is part of the crust that was melted away in the area. Now, if one then goes on the other side of the Yucatan platform and look at the deposits that are on the floor of the Gulf of Mexico, one gets into a scenario where those deposits are known to be up to 200 meters thick. This was discovered from some of the early deep-sea drilling project drilling in the floor of the Gulf of Mexico. And these are basically fractured, shallow water limestones. The source of these is believed to be the Campeche escarpment. And if we then look at the distribution of samples in the Gulf of Mexico and follow recent work by Dene et al., it turns out that something like 43 to 115,000 cubic kilometers of material fell off the escarpment face in this particular event. This is the largest landslide deposit that is known on Earth by an order of magnitude. Really big event. I might also point out that that star down in the lower corner is the Reforma trend in Mexico. This happens to be one of the giant oil fields in the world, and they're actually producing oil from breccia that was associated with the Cretaceous Tertiary landslide deposit. And then if one thinks about what happened that day, there presumably was a massive shock wave that propagated down through the ground. It would have reached the edge of the escarpment within seconds of the impact, and presumably it blew off a section of the escarpment face. The curious aspect of this is if you calculate how much of the escarpment face must have retreated in order to have generated these deposits, it takes something like 10 kilometers of the escarpment face to have retreated in this event to generate these deposits, which is a huge volume. Now, that is the curiosity part of this. We have been interested in finding these deposits, getting closer to it, and sampling nearby to learn more about what happened in this event. The reality is the existing bathymetry before this effort was completely inadequate to launch a modern expedition. We're based upon the satellite bathymetry that was the best that was available at the time, and simply had no way of knowing whether there were going to be any outcropping sequences there or at what level to look. So that was our goal at the outset, and during this cruise, we mapped a 635-kilometer long section of the escarpment. This is equivalent of mapping from the Big Island of Hawaii to Kauai, and it's really an area of spectacular relief. I'm pointing out as that goes by, you're seeing something like 80 submarine canyons. Before we did this, we only knew of 3, and this whole face is all carved up with major canyons. Now, getting back onto the topic, though, of where the KT deposits were, it happens that fortuitously, the deep-sea drilling project in 1971 drilled 2 holes on top of the escarpment. And this is a great example of sample and data archiving that was done where the information about this drilling is well recorded. And at the time, they had no idea that there would be interest in the Cretaceous boundary in this area. They drilled through holes on what they thought were gullies on the face of the slope, drilled down through a nearly continuous tertiary section into these deposits that were hard drilling. And they got less than 1% recovery in the samples drilling into this, but it consisted of chips of Cretaceous limestone, so we know that they got into the Cretaceous of that, and it had this fused material in it, which we now know are probably ejecta or metamorphosed samples along the escarpment face. Now, if you then project where these boreholes were drilled, onto the multibeam data that the Falkor collected, one finds that at the level of the top of the Cretaceous, just projected a very short distance, one finds that there's a distinct break in slope along this escarpment face and the like. And it corresponds remarkably well with this. It's steeper below this in the Cretaceous section. And the same thing happens at the other edge of the escarpment. And based upon this, I think we know where the top of the Cretaceous section is there, outcropping to very close a level. Now, like any data set like this to where one collects a lot of information and maps a big section of it, there are all kinds of curious things that are going on. One of the things that we've discovered on this is there were large landslide deposits that are also in the tertiary section. Other people are now modeling these landslide scars as being possible tsunami generators for things going into the U.S. Gulf Coast. I myself am particularly interested in these box canyons because they're rather bizarre, and there are about 80 of them. You note that this canyon has no central valley to it. But the reason I'm showing this slide is the floor out in front of this escarpment is filled with flat-lying sediment. This is the Mississippi River fill, and it has accumulated about 3 kilometers of sediment and burying most of the base of the escarpment. It happens that there are a few places where there's an apron out in front of the escarpment face where there's some big blocks, and the block you see in this screen here is more than 10 kilometers across, and those appear to be pieces of the escarpment face that have not been buried yet and are telling you something about the size and the scale at which the escarpment broke away. Now, I think that this cruise got us exactly what we wanted to know. We wanted to know where the face was so we could go back and sample it. There are clearly outcropping exposures that are available. I think we know the location of the KT boundary here within probably 50 meters in X, Y, and Z and the like, and it is providing us a roadmap that will allow some group to go back and make that available for sampling. I think it's obvious that this data set is going to make some group will do this at some point. Now, I make another comment, and there's a lot of interest in the data handling here, and it's an interesting experience in doing the data sharing. We have provided this data to Google already. It's up on Google Earth. If you scan in on the escarpment face, you'll see it's now one of the best map sections of the world. You have to zoom in on it in order to see that, but if you wanted to work on the escarpment, there it is, it's available. We've also provided the full swath data already to 3 groups. One of them includes a group in the USGS that we're actually not explicitly working with. We've got the full data, and 2 groups in Mexico. And we have a personal goal to get these data to the national data centers before AGU this year, so we've fully released the data. What I'm talking about here, multibeam data, swath data, data of resolutions that can be gridded at 100 meters or better, represents a very small portion of the world ocean. In fact, only something like 5% of the world ocean has been mapped at anywhere near this level of resolution. And if one were to calculate how much of an effort it would be to map the entire world ocean at this level, it would take something on the order of 400 Falkor years at sea to do that. Now, obviously, it's not going to happen with a Falkor. But I would maintain that every one of these data sets that's collected becomes the roadmap and the springboard for other types of research. And I'm in a way, see this as when you collect the surface ship data, it opens up the opportunity for collecting other data types, and then it opens up the opportunity for sampling in ways where you really get the science out of it. And the multibeam itself is just the enabler of these other forms of research. Now, my next example of how a collection of multibeam data has stimulated a significant amount of research is springboarding up to the Arctic, and I'm focusing on a sector in the Canadian Arctic and the Beaufort Sea. And this happens to be an area that was drilled extensively in the 1960s and 70s by oil companies, obviously prospecting for oil. But as a consequence of that, they determined that there was significant amounts of permafrost underneath the whole shelf in this area. They have enough data in this area to actually contour the thicknesses of the permafrost, and in some places it's up to 500 meters thick. I might also point out that this area it distinguishes itself also because there are known to be substantial gas hydrate deposits in this area. These gas hydrates are a crystalline form of water and methane that is believed to store a whole lot of methane globally, a lot of research interest in that topic. Now, I would maintain, though, that the grid of multibeam data that's sort of illustrated there in the color on the top of this diagram has really caused us a springboard of a lot of information. And the driving theme behind this, the concept behind this, is global change, thermal warming. And I maintain that this part of the Earth is unequivocally undergoing the most dramatic thermal change of any place on Earth. Now, contrary to your immediate instincts, the change that I'm talking about here is not the recent anthropogenic change. It is the change that happened at the end of the last ice age when we flooded a truly frigid permafrost region with relatively warm Arctic Ocean water. Now, the waters the permafrost conditions at in the ice age probably were minus 15 degrees centigrade mean annual temperature, and the water that came over it is no colder than minus 1.8 degrees. Consequence of that is you've got more than a 10 degrees C thermal wave propagating down into the ground now. And this topic has been one of considerable interest in sort of how this plays out and what it means for the gas-bearing deposits that are entombed in the sediments. And for one reason for this is if you look at the thermal profiles going down in the ground, they're going to change with time. But the conduction of heat in the ground is rather slow, and we still haven't recovered from this thermal event. That thermal wave is still propagating down into the ground, and it's going to have implications for the decomposition of gas hydrates in this area, which would be decomposing at the top and the bottom of the gas hydrate field, and we would have permafrost thawing at the base of the stability zone. So, both of these will release methanes. Both of these have the capability of releasing significant amounts of methane. There's a tremendous amount of interest about methane released in the Arctic right now, and one of our issues is we cannot distinguish between what was going on before man perturbed the Earth and what was something that's a natural process that at the heart of understanding processes going forward. And I maintain that the multibeam data that was collected in this particular area, where we know the permafrost and gas hydrates are there, has been very powerful in being able to advance our understanding of at least what's ongoing in this area. And I'm going to show you 3 examples where gas is coming out of this system. I'm first going to show you one in the mid-shelf, then I'm going to show example from this what's called the shelf edge seep zone, and then I'm going to move down in slope and talk about expulsion features on the slope itself. And I'm going to start off here with one place which is a morphologic feature. We were attracted to this bump on the seafloor in there because it's a very distinctive place and the like. We did not need to hunt at random through the Arctic and the like, and can use a small ROV to very directly sample in the bottom. And if you're looking at that video, you can see that gas is coming out of the seafloor in a fairly robust way. Now, those clouds of sediment are not in the water column because we stirred it up with the ROV. That gas is coming out of these features fairly vigorously, and up until this time, we had no evidence of where gas was coming out on the shelf. It is clearly venting, and in places, it's venting in a fairly significant way. Now, the next comment I'd like to make is about the shelf edge. And the shelf edge is a particularly interesting place because right along the 100-meter contour is where you'd expect the permafrost to be decomposing in this area. Now, the multi-beam data that was collected here, like a lot of places, now has the capability of imaging in the water column, and things which are potentially gas plumes can be detected in mid-water. And for these the soundings that are shown here are in red, and places in the water column are shown as blue, and these are pretty clearly little plumes coming up off the bottom, and it looks like a lot of gas is coming out. But one of the things that then one can go back to and look at in more detail is just to look at the bottom with an ROV, and it's very instructive. yes, there's gas coming out of this area, but it's only little bits of gas. Comes out a hole, and then a little bit later, gas will come out of another hole in a different place, and it's small amounts, but it's going over a wide area. So we get a bit of a problem. It's a very different style of the gas venting, which is coming up on the middle of the shelf, but we're able to see, yes, this process is going on, and we couldn't have known that without the multibeam data. The other aspect, I've just been talking about that shelf edge seep zone, and I've been pointed out that this is about where the edge of the permafrost would be. The edge is predicted to be right around the white contour, which is the 100-meter contour, and I would point out that this is a remarkably unstable shelf edge here, the feature that is clearly falling apart. That does not mean it's correlated with where you'd expect the permafrost to be decomposing. It doesn't mean that it's causally related, but it's suggesting that there's a smoking gun between these two processes, and this is one of the things that has stimulated multiple research groups to come to this area since the multibeam data was collected in 2009. Now, I want to finish in the Arctic section by just showing you two features that are expulsion features on the slope. These features are big enough to be picked up on multibeam, surface ship multibeam data. But for the rest of this talk, I'm going to go to the next level of resolution. I'm going to start talking about multi-beam data that is collected on surveys using a mapping AUV. This mapping AUV is capable of collecting, routinely collects 1 meter grids of multi-beam data. It's a whole another order of magnitude improvement in our ability to image the bottom and the like. And for the rest of this talk, I'm only going to be pointing out features that are fairly subtle on the seafloor that we really couldn't see with surface ship data. And although these, this is two images of the same area, these are mud volcanoes. The top is no vertical exaggeration. The bottom has got a vertical exaggeration on these images and the like. And first of all, I'd like to point out that these are very low relief features. And if we look at the same data in map view, one of these is sort of comes to a pinnacle, a little cone, and the other one is a flat-topped feature. And there's very little surface relief on there. But when you put side scan data on top of this, you can start to see these areas that are outlined as flows that are coming out of it. And we can't see that in the bathymetry itself, but we can outline where there are flows. They seem to be emanating out of two places in this area. Most of them show up as being white in this illustration. Curiously, if you look at it, there's the one that's black here. Rather obviously, it's cross-cutting other ones. That's clear, the candidate for being the youngest flow. And we now get into the level where we can map features in a time scale which we think might be capable to repeat map in this area to be able to track change with time. If one looks at the other mud diapir that we surveyed, and I might point out, we collected these surveys on October 4th of this year, fairly new data. And I'm just going to zoom in on the boxes on top of this feature. And this is the clippets of data. To your left in the color code is bathymetry. And the point I'd like to make is that whole color code is covering a depth range of just 4 meters. Very detailed range, and those contours are 25 centimeter contours. So we're starting to get data that has fidelity to that level. And if one looks at the side scan data that's collected simultaneously with it, you again get sort of patches of color-coded material that's there, and one can then go look at these areas with a ROV, and it turns out the seafloor is remarkably different in these sites. And particularly note, most of the backdrop of this feature consists of beds of extensive tube worms. Those are probably chemosynthetic worms. The bacterial mats interspersed with it. There's a little methane that bubbles out of them periodically. But the curious thing is when you go into that white and black area, the seafloor is devoid of sessile organisms. That's probably because these things have erupted so recently that the bottom is not yet colonized by organisms. And again, this is a sort of a candidate for repeat mapping efforts in this type of area. Now, I finally want to make a few points about Monterey Bay. And MBARI collected a grid of multi-beam data in Monterey Bay in 1999, knowingly that it would be an area that operate in for some time. And I think it was one of the best investments we made as an institution, because this has occurred in hundreds of publications and probably 1,000 talks that have gone on that have used this as the backdrop. That's been great. But more recently, we've been mapping using the AUV in this area. In fact, there's about 30 AUV dives that are shown in this composite of red lines that are down at the bottom here. And one of the things that we've discovered is we just didn't see the canyon correctly with that level of resolution. It's the next level of resolution which really becomes important and insightful. And this is one example. This is a site about 1,800 meters water depth. I'd like to point out that if you don't see anything of particular interest in that slide, you're not supposed to. It's pretty flat-floored area, but that's the best we can do with that level of data. But if you superimpose the AUV data on it, you discover that the bottom of the canyon is every bit as complicated as the floor of any river system on land, and there are a number of fairly significant bed forms that are going on there. These are features that are about 5 meters high, 100-meter wavelengths that are on the floor here, and we simply didn't know they existed before. You could look at them and infer that they might be sand waves going down. But the next level of discovery simply comes by going and looking at the bottom with an ROV, and you quickly discover these bed forms are made up of refrigerator-sized boulders. And so this has been incredibly eye-opening to us about how the canyon moves material from land out into the deep sea. So that's one point. Next point about multi-beam data here is we are getting at the level that allows us to do repeat mapping. And we're able to get repeat mapping of geologic features that are actually changing enough in time and have the resolution to track these changes. And this is one section of the canyon that we've mapped multiple times. And this is an image of the data there. That's actually the same segment of data shown top and bottom. On the top is just a topographic view. Below that is a slope map. I'd like to point out that, again, that's got 25 centimeter contour level on it. And at this level, those bed forms that you see in the bottom of the canyon still have fidelity at a 25 centimeter level. And this is a place that we mapped early in our AUV program 4 times, and because we've mapped it 4 times, we can make difference maps of these areas, and in those difference maps, you can see change in the bottom. Now, I might point out that to your left, there is the colors code of how much the bottom has changed or appears to change in the difference map. And along the very edges of these scripts, you see that there's some bright color on the sides. That is pretty clearly associated with errors in the navigation. And to get at this level, errors in the navigation of 1 to 2 meters in this can explain the changes on the sides of the canyon. But the floor of the canyon there is that green color and basically indicates that we were able to make difference maps in that time framework, which didn't change. You move to the next spot in there, That's a 25 days later. Turns out that there's been a big storm in the meantime and the like. And this data shows that the bottom has changed very appreciably. Some areas have gone up 2.5 meters. Some areas have gone down 2.5 meters. And more change happened in that interval than the next one, which was 110 days later. I point this out because we are now able to measure changes of geologic processes with these mapping tools. So we're getting into sort of things where we're now able to do, in a way, 4D studies of at least major features that are going on. But to get into things that would be able to track change, perhaps at a biological level, we need to go to still higher levels of resolution and the like. And this cartoon shows the level of resolution at the top that we can get from the existing mapping AUV, and below shows what are attempting to get in the ocean imaging project that Dave is championing. We're trying to get quantitatively correct maps of the seafloor at the 5 centimeter grid resolution with about 1 centimeter vertically. And this is pushing the edges of resolution. And this slide shows a cascade of multi-beam data, starting off with 30 kilohertz data, surface ship collected data that's at the top where you sort of would map the whole canyon. To the right on the top is the next level is one AUV survey. We surveyed the bottom one day in here. There's not a lot going on the bottom there. It's pretty flat until you zoom in on it and blow up the area which is in the lower left. And there you start to see, again, we've got features on the bottom there that are approximately 100 meters in wavelength, 1 to 2 meters high, that we simply didn't know they were there. They clearly got something to do with the processes in the canyon. And more recently, we've surveyed just part of one of these bed forms with the data that's shown in the lower right. And I'm just going to show that one more time. This is now a 5 centimeter grid resolution. Clearly shows that the side of this feature has got all these waves that are there. We didn't understand that they were there before, and this is a test, and it's literally the first place we've taken to this level of resolution. This is a 5 centimeter contour level on it. The data has fidelity at that level in these bed forms. But that's the acoustic data that's there. The real goal is to try to integrate the bathymetry with the optical information of putting the bathymetry together with the imagery. And this is a first attempt at this. You can now see this is a photo mosaic, which is collected in a quantitatively correct way that is imaging this, and the images are superimposed correctly on the bathymetry. And I point this out because we are now getting to the level here of mapping where we can track biological change on the seafloor, and it's sort of one of the goals to utilize that. So, just in summary, what have I shown you here? I think I've given you an illustration of what went on in one Falcor cruise. I think that sort of data is just a roadmap which you can use for other purposes. And every time you do this, you enable research in the areas on these topics, and you can keep cascading down on these levels. And I think we're now at the point where technology is really coming online, where we can start to collect stuff which is kind of like Google Street on the seafloor. And that's a direction that we, and I guess other groups, are going to. So thank you.
Thank you very much, Charlie.
I'd like to make one final comment that I really would like to thank the Schmidt Ocean Institute, both for executing an excellent cruise, very beneficial to us because it was our dream, but more than that is the larger image of, and the larger effort of, trying to stimulate oceanography in a general way and providing new access to the ocean for a large and open community.
Thank you so much, Charlie. While in the next 3 to 5 minutes we're preparing to the final panel for the day, I wanted to go over a few items that will be happening in the next few hours.